Hi, my name's Ryan Kohls, and I worked with Joshua Grassel. We're both industrial engineering students at Cal Poly San Luis Obispo. Our research focused on production planning in integrated circuit supply chains. We chose to focus on integrated circuits for two main reasons. The first being the huge importance they play in enabling our modern lifestyle. They provide the computation that powers everything from our phones to our laptops to our vehicles. This is especially significant within California, as all the largest IC designers like Intel and Qualcomm are headquartered within California. The second reason we chose to focus on integrated circuits is their manufacturing difficulties. They have a long process of very complex steps that take place in a tightly controlled clean room environment, where even a slight fluctuation in temperature or a single speck of dust can ruin an entire batch, leading to a very high scrap rate. On the left, we have a picture of a wafer, which is how integrated circuits are manufactured, with each square representing a different IC. On the right, we have a heat map of the defects, with each color representing a different kind of defect for an integrated circuit. The orange, for example, may represent a small scratch, in which case the IC would be thrown out. But the pink may represent a memory issue. In that case, these ICs would be sold as a lower performance product at a lower price. The process of categorizing ICs based on performance is called binning. Our research focused on production planning, which is deciding how much to produce and where to produce it. The standard technique for this is Material Requirements Planning, or MRP, which is taught as the standard in engineering and business classes. Unfortunately, MRP fails for IC supply chains because MRP doesn't account for yield or binning. I was introduced to this problem at an internship where I was asked to plan production for a $45 million supply chain that had frequent stockouts costing millions of dollars. And I was asked to develop a better model that accounts for binning using statistics and programming.
Because binning is such an important problem to our project, we are first going to start by explaining it through an example. In this example, we'll be talking about a guitar manufacturing company. The process would originally be ordering 10 blocks of wood. One of these blocks of wood comes in with holes in it, so you can't use it for making a guitar, but the other 9 are good. So those 9 you turn into guitars, and you sell to the 9 customers. However, let's say 20% of these blocks of wood come in with these unsightly knots on them. Your new process would look like this. You'd start with the 10 blocks of wood. 7 of them would be good. The one would have the holes in it, which is unusable. But then there are these 2 that have knots of wood, that have knots in them. You take the first 7, make them to 7 guitars as previously, but with the other 2, and you make them into guitars, they don't look as nice. So what you can do to alleviate this problem is just paint over them. So now you have a guitar that might not be worth as much, but is still sellable. Those first 7 you sell to your 7 customers, and the next 2 you sell to 2 other customers for a lower price. A special case of this is, let's say you know in a certain time period you'll only sell 5 of the nicer, more expensive guitars. You can even use some of your nice blocks of wood and paint over them to make them into a lower quality guitar if you know that you couldn't have sold them anyway. How this ties over to binning is that nice block of wood would be a bin A, or high performing bin. The one with knots in it would be a bin B, or a low performing bin but still usable. And the one with holes in it would be bin F, failed or scrapped.
The main performance metric we're using to evaluate the quality of our models is service level, which is the chance of having the right product in the right quantity at the right time. In other words, it's the chance of a store being out of stock of the product that you want. This is the key performance indicator with production planning, with most companies having a target service level of 95%. Currently, material requirements planning is used throughout industry to plan production, but unfortunately it fails for IC supply chains. We're proposing discrete event simulation as an alternative tool for production planning. Discrete event simulation involves setting up a model and running hundreds of thousands of different scenarios to figure out what gives you the best results, making it much more flexible and accurate than MRP. We developed our discrete event simulation within Python.
After finishing our statistical and discrete event simulation model, we wanted to test it on a supply chain. So we started off with one IC supplier that has a binning A rate of 40%, a binning B rate of 20%, and a failure rate of 40%, which is not uncommon. After ordering from the supplier, some of the items will go to bin A, some will go to bin B, and some will go to scrap based on the randomness. We'll have 2 example assemblers that would have demand for these ICs. For example, Dell has a demand of 20,000 units of bin A, so the high performing bin. Lenovo has a demand of 10,000 units of bin B, or the lower performing bin. However, just as with the guitars, the special case is if we have excess bin A units, they can be substituted for a lower performing bin and be given to Lenovo. After we ran the discrete event simulation, we plotted the results. On the x-axis, we have the order quantity from that IC supplier, and on the y-axis, we have the service level or the likelihood of meeting the demand of that assembler. We'll start off with Dell. It has a service level line that follows this. Just as we expected, the more we order, the more likely it is that we meet the demand of Dell. Lenovo has a service level line like this, and this one is slightly higher because of that special case. When you had excess of the bin A, it could have been substituted as a lower performing bin and given to Lenovo. However, if we had excess of bin B, it could not have gone the opposite. We couldn't have substituted that as a higher performing unit. The ideal quantity for the 95% target service level we have is 87,000 units. After running this, we wanted to test it on a more complex supply chain. Supply chain 2 has an international supplier. This supplier has all the same stats as the previous supplier, but has a price of $1 per unit. We also added a domestic supplier. The supplier has a bin A rate of 70%, so much higher than that of the international supplier, a bin B rate of 20%, and a failure rate of just 10%, much lower, but with an increased cost of $1.50 per unit. Just as in last time, after we order some from these suppliers, by the randomness, some will get sent to bin A, some to bin B, and some will be failed. We had the same two assemblers as last time, Dell and Nova, with the same demands. This is plotted a little bit differently. On the x-axis, we have the order quantity from that international supplier or the same supplier as in the first supply chain. On the y-axis, we have the order quantity from the domestic supplier, the new one that costs more and has a higher binning A rate and a lower failure rate. We plotted the service level lines. These look a little bit different as each line represents an individual service level. These represent 5, 50, and 95%. Plot for Lenovo looks like this. Looks a little different because they required a different bin and a different quantity. After putting both together, we define this space as a space that we can work in because this is where the 95% service level is met for both of our assemblers. But within this space, we want to choose the point that has the lowest cost. So in the background, we have the cost gradient, green being the least expensive and red being the most expensive. We can find a part in that upper curve that the 95% service level is met and is the most green. Turns out to be about 20,000 units from our international supplier and 26,000 units from the domestic supplier, with a total cost of $59,000. So keep in mind, the last time when we only had the international supplier, our ideal units came out to 87,000 units, which was a cost of $87,000, much higher than when we added in our new supplier, because even though our new supplier cost more, we had a higher likelihood of meeting those demands with the higher binning A rate and the lower failure rate.
In conclusion, MRP fails to accurately plan production for IC supply chains, so we developed a discrete event simulation model that provides highly accurate and flexible production planning solutions. As part of our research, we also developed two other methods, a statistical model and a linear programming model, which each have their niche uses, but overall we recommend discrete event simulation as a very flexible tool. Our next steps are verification and validation. We want to prove that our research methodology was sound, so we submitted our work for academic publication where it was accepted by the Institute of Industrial and Systems Engineers. The next step was industry testing, where we implemented one of our models in a real-world environment to see how it'll perform over the next few months. The last step would be incorporation into the curriculum. While currently MRP is taught as the standard in engineering and business classes for production planning, we think that our discrete event simulation model could be taught at a more advanced level for handling these niche cases, such as integrated circuit supply chains. And finally, to improve the accuracy of our models, we'll need to incorporate inventory levels, which would represent companies using warehouses. Thank you for listening to our presentation.